In this lecture, we want to study work and energy for 2D rigid bodies. So this would be along the same line that we had for particles. For particles, we studied the kinematics, the kinetics, and then work and energy. And we saw that work and energy is basically a powerful method to solve some problems, not all of the problems, but it is very powerful in a sense that it makes our life much easier in solving some of the dynamic problems for particles. And then for rigid bodies, we had the kinematics, which was just in general case for 3D kinematics. And then we studied the kinetics of 2D rigid bodies. And now that we are done with that, it's a good place to study the work and energy for rigid bodies, but again, 2D rigid bodies. So before getting to work and energy for rigid bodies, we have to be able to calculate the kinetic energy for a 2D rigid body. So for a particle, we knew how to calculate the kinetic energy. It was basically T is equal to 1 over 2 mv squared, velocity of the particle. But for a rigid body, we have to derive an expression based on this equation. We have to derive an expression for the kinetic of rigid body, because a rigid body consists of many points. So, and we know that each point can have a different velocity. So this equation is not true for rigid body, and we have to start from this equation for a particle and derive the kinetic energy for a rigid body. And then when we are done with that, we can use the work and we can state the work and energy principle for a rigid body and solve some problems. So our goal here in the first part of this lecture is to derive the kinetic energy for a rigid body, for a 2D rigid body. So let's say we have a coordinate system here. So this derivation would be, again, similar to the derivation that we had for deriving Euler equation for 2D rigid bodies. It's basically, we have a coordinate system, a general 2D rigid body that we have the velocity of one point of that rigid body. And then let me actually draw this. So let's say this is our coordinate system. We have a general rigid body here, and we have the velocity and acceleration of one point, mainly velocity here. So, and that point is just, let's say, is this point O on the rigid body, and we have we attach a frame to the rigid body on that point. So this point O, we have its velocity on the rigid body. So this is our inertial coordinate system, X and Y, and here we have X and Y. So this is a rotating frame attached to this rigid body that moves and rotates with this rigid body. So here the rigid body is just rotating and also moving, it has a linear velocity and also an angular velocity. So the velocity of this point O, we have it. So we assume that velocity of point O is given. So this would be, for example, Vox I plus Voy J. And now we want to derive the kinetic energy. So let's consider an element on this rigid body. Let's consider a point-like element on this rigid body. For example, this point here, a small mass that is dm, and we call this point P. So for this point P, because it's a point-like mass, I can write down the kinetic energy with the formula that we had for particles. So this would be the relative position vector of P with respect to O. So this is R. So for P, I can say that T is equal to, or dt is an element of kinetic energy here for a small particle P belonging to the rigid body. So dt for that small particle would be 1 over 2 d Vp squared. And so we can write down this equation based on kinetic energy for particles. And the key here is that, the same way that we had for derivation of Euler equation, to write down the velocity of this point P based on point O. So I can say that velocity of point P is equal to, so Vp is equal to Vo plus omega cross R. This is Rp with respect to O, this R that we have here. So let me actually kind of use this equation that we have for Vo and expand these terms. So I can write down this is equal to Vox, the I direction, plus Voy, the J direction, plus omega. So because we are in 2D, omega would be a scalar quantity times in the k direction. So this would be omega in the k. This could be positive or negative. Cross Rp, so this would be, let's say, x in the I direction plus y in the j direction. So basically we are saying that R is equal to x, the I direction plus y in the j direction. So let's simplify this. I can write down this is equal to Vox, and for the I direction here, k cross j would be minus I, so I can say minus y omega in the I direction plus Voy plus k cross I would be j, so here we have x omega in the j direction. And now we can substitute this value, this quantity for Vp into this equation. So I would say that Vp, so the magnitude of Vp, when we say Vp squared, this is what we mean here. So Vp squared, this is basically the magnitude of velocity vector at point P squared. So this would be Vox minus y omega squared plus Voy plus x omega squared. And this would be, so I just expand the square that we have here and kind of like reorganize the terms. So I can say this is Vox squared plus Voy squared. So this would be Vox squared plus Voy squared plus, here we have also y squared, omega squared, x squared, omega squared. So I can say omega squared plus times omega squared times x squared plus y squared. And then we have the last terms for both of these parentheses. So that would be minus 2y omega Vox and plus 2x omega Voy. So let's just go with this term first. 2x omega Voy minus 2y omega Vox. So this is basically Vp squared. And now I substitute this quantity for Vp squared into the equation for kinetic energy that we had. And then we, what the next step is. We have to do integration over the whole rigid body to calculate the kinetic energy of the rigid body. So here we have dt is equal to 1 over 2 dm Vp squared. So right now I just write down Vp squared, but we want to substitute this quantity into this equation and then do the integration. So let's do the integration here. If we integrate this here, we have to calculate the integration of this term. So the integration of dt, the sum of all the kinetic energies of the particles on the kinetic of the elements of the rigid body would be the kinetic energy of the whole rigid body. So the integral of dt would be t for the rigid body is equal to, we can bring out this 1 over 2, and then we have to do this integration. So this would be Vox squared plus Voy squared dm. So Vox squared plus Voy squared dm plus, here we have omega squared integral of x squared plus y squared dm. Because omega is constant, doesn't depend on x and y, we can bring it outside of the integral. So, and here we have plus 2 omega Voy integral of x dm, and the last term is minus 2 omega Vox integral of y dm. Okay, so this is equal to. So again, Vox and Voy, they don't depend on x and y, so we can bring it outside of the integral, and this would be integral of dm, which would be the mass of the whole rigid body. So this would be 1 over 2, here m, and here is basically Vo squared, because this is the x component of Vo, this is the y component, so I can say that this is equal to Vo squared, which these are the same terms basically. Plus, here again we have this integral. Now we are familiar with this integral. Integral of x squared plus y squared dm in 2D, that would be the second moment of inertia for the rigid body. So this would be I, or omega squared. We had omega squared here and I here, and this I would be about point O, because x and I are measured with respect to point O here. Remember, the origin of this coordinate system is at point O, so we should denote that by IO. So this would be omega squared IO plus, here we have 2 omega Voy, and we are also familiar with this term. This is basically mx of g, the x coordinate of center of mass for the whole rigid body, because remember, so just a side note here, xg was x dm over m. So now we have this integral, which would be m times x of g. So this would be m xg, and this term would be minus 2 omega Vox, and similarly this term would be m yg. Okay, so far so good. So let's clean this part. Okay, so therefore the kinetic energy is equal to T equal to, so this would be 1 over 2 m Vo squared plus, this would be 1 over 2 IO omega squared, and then we have plus, so we can cancel these 2's with each other, so we have these 2 coefficients here and 1 over 2 here, so they cancel out, and then we have I can factor out m omega, so this would be xg Voy minus yg Vox. So this is the equation for kinetic energy of a 2D rigid body. So you can see that, we have again these extra terms. Sometimes you see that people just write down these two first terms, 1 over 2 mv squared plus 1 over 2 omega squared. But we have actually this extra term. And again, similar to the process that we had for deriving Euler equation, here we can see some special cases that we can simplify this equation further. So the first special case is when O is equal to G. The point that we consider O here, if that point is actually just the center of mass for the rigid body. If that's the case, then x of G is equal to y of G is equal to 0. And we have T is equal to 1 over 2 mvg squared plus 1 over 2 ig omega squared. And again, this equation is always true whenever our reference point is just center of mass for the 2D rigid body. You can see that here is just a linear component of kinetic energy, and this is the angular component. So this is kinetic energy due to linear velocity. This is kinetic energy due to angular velocity. So that's the first special case that we can simplify this equation. The second special case is if O is stationary. O is doesn't have any velocity. The velocity of O is 0. So if 2VO is equal to 0. If that's the case, then VOX is equal to VOY is equal to 0. And here we get T is equal to 1 over 2 m. Actually, the first term is also 0 here because VO is 0. So this term would be 0, this term would be 0. We have only 1 over 2 IO omega squared. So IO omega squared. And the third case that we can simplify that equation for kinetic energy is when VO passes through G. So in that case, this parenthesis would be equal to 0, because if this parenthesis is equal to 0, we are going to have x of G over y of G is equal to VOX over VOY. And that means the velocity of point O passes through the center of mass. So this means VOX over VOY is equal to x of G. This is y of G. This is what we mean by saying that VO passes through point G. And if this equation is true, that parenthesis is equal to 0. And we only have these two terms here. So for this case, T would be 1 over 2 m VO squared plus 1 over 2 I O omega squared. But again, notice that this equation is not true at all times. It's just, this is true if and only if that the velocity of point O is equal to 0. Otherwise, if we want to stick to this format for kinetic energy of a 2D rigid body, we should always consider the center of mass. We can always write down this equation for center of mass, no matter if it is stationary or not. So this was the kinetic energy for a rigid body. And now that we can calculate the kinetic of a rigid body, we can use the work and energy principle for solving dynamic problems on 2D rigid bodies. So remember, work and energy principle in its general form was the work of non-conservative, so not omega, so work of non-conservative forces, conservative forces was equal to E2 the energy of system at state 2, final state, minus the energy of system at state 1, initial state of the system. And we said that basically for us this would be T2 plus U2, which T was kinetic energy and U was potential energy, minus T1 plus U1. So these T's are kinetic energy, and U, again, they are potential energy, which for our problems, there are only two sources for potential energy. One is just a spring, the other is gravity, spring and gravity. So we had this before. This is true also for rigid bodies, and the key here was to be able to calculate T for a rigid body, and now we have the equation for calculating the kinetic energy of rigid body. So with this derivation, I will start solving some problems. This is the first example that we want to solve here. So the question is, find the angular velocity of half disk when AB becomes horizontal. Assume pure rolling. So we have half a disk here that if we just leave it on its own, it starts to rotate because the center of mass is somewhere here. And because of the gravity, so here we have, let's say this is the direction of gravity, G. Because of gravity, the disk is going to rotate. But on top of that, if we just leave the half a disk to like in this position, it's going to roll to go into this position and just continue to rotate. But we are also on top of the gravity, we are also giving an initial velocity to its center. So it's basically like the half a disk is in this position, and we just leave it, and at the same time that we leave it, let's say we are holding it in this position, and then we let it go, and at the same point we just, for example, we hit the half a disk with a hammer here to give it an initial velocity in this direction, and we want to find the angular velocity of the disk or half a disk when AB becomes horizontal. So this, after we let the disk go and we give it an initial velocity, the disk starts to rotate, and we want to find the angular velocity at this position. The mass of the disk is 4 kg, or the radius of the disk is 3 meters, and the initial velocity is 2 meters per second. So here, because we have pure rolling, basically the force of friction doesn't do any work because pure rolling, the friction in pure rolling is basically a static friction. It's not kinetic energy. So therefore there is no energy dissipation due to a static coefficient in the system, and therefore we can use the conservation of energy, or just work on energy principle in general, and say that the work of non-conservative forces is equal to 0, and therefore we have the conservation of energy. So we can say that W non-conservative forces is equal to E2 minus E1. And here again, because this is pure rolling, if we had a skipping here, a sliding here, because the type of friction would be kinetic friction, then we have a non-conservative force in the system. But again, because this is a static friction, the force of friction doesn't do any work. So this would be equal to 0. So W and CF is equal to 0, and therefore E2 is equal to E1. So now I can say that this is the initial state, for example, 1, and this is the final state, E2, and calculate these energies to see if we can find an equation on the angular velocity at this moment that AB is horizontal. So here basically, let's say this is the angular velocity, which is unknown. So let's calculate these terms. So for E1, I can say that E1 is equal to T1 plus u1. Let's calculate t1. So t1, first I have to find a reference point that I like to consider for calculating the potential, the kinetic energy. So I would say here, because we don't have because we have pure rolling here, so I would say that the velocity of this point A is equal to 0. And we saw that if the velocity of point A is equal to 0, we can write down the kinetic energy of this rigid body as 1 over 2 IA. So this would be 1 over 2 IA omega squared. Because this is true because A is stationary. Or I can say that this is equal to also 1 over 2 m Vg, velocity of center of mass, squared plus 1 over 2 Ig omega squared. But you can see that this is easier to calculate. So we go with this point, with point A. So here I have to calculate IA and also omega squared, because basically here we have the velocity of center of mass, but we don't have omega. So let's call this omega 2, for example. This is omega 1. But based on kinematic, we can find omega 1. I can say that I can write down the velocity of this point, which let's call it O. I can write down the velocity of O based on A. And because I have the velocity of O, and also I have velocity of A, which is 0, I should be able to find omega 1. So basically VO is equal to VA plus omega cross R A with respect to O. Which basically here omega turns out to be, because it is in the counterclockwise direction, here we can say just R omega. This is also instantaneous center of rotation. So I can say that the velocity of this point would be R times omega. So VO is equal to R omega. And because it is in the counterclockwise direction, it would be negative. But that doesn't matter for calculating energy because we have to square omega. So here basically omega is minus V minus VO over R. And if you do the vector calculation, you find out that minus for omega. But again, that doesn't matter. We can say that the magnitude of omega is just V naught over R. So this is for omega. Also, I have to calculate IA. And finding IA is a little tricky because, so for a half a circle, remember that we said that this moment of inertia for half a circle around its center is 1 over 2 mr squared. We had that when we were studying the kinetic of rigid bodies. So for a half a circle, let me draw a half a circle here. So let's say this is a circle here. And let's just, for example, erase half of it. So this is the kind of like half a disk that we have. Oops. No. It's not drawing that line here. Let me see. I should be able to write down here. Oh, it's because on the eraser. Okay, so this should be, yeah, this is the half of circle that we have. And we set for this half of circle here, let's call this point O. We said that IO is equal to 1 over 2 mr squared. But here we want the moment of inertia at this edge. So let's say this is point A. We want to see what is the moment of inertia around this point A, because this is basically what we have here. We have to calculate the moment of inertia for this disk around this point A. So in order to do this, we had also parallel access theorem. So for parallel access theorem, we said that we can calculate the moment of inertia about one point by having the moment of inertia about the center of mass. And the point here is that we don't have the moment of inertia for about the center of mass for this half a disk. So in order to go from O to A, first we have to go from this point O to center of mass for this disk. Remember, O is not the center of mass for half a disk. It is center of mass for a full disk, but for half a disk, point O is not the center of mass. So we have to find the center of mass, then go from point O to center of mass, and then from that center of mass, we can go to point A. And for a half a disk, we know that the center of mass is basically somewhere here. Because we have symmetry in the x direction at least, it should be on let's say we have a coordinate system here. Let me draw actually the coordinate system here. So let's say this is x and this is y. So we know that because we have symmetry about y-axis, the center of mass would be somewhere along the y-axis. So the x component of the x component for the position of center of mass would be 0, but for the y component we have to find it. So let's actually do that, because we also need the center of mass, the location of center of mass for half a circle when we want to calculate the potential energy. So here I would say that if you already know the answer, that's fine, that just you use it. I think it's 4r over 3 pi, but the calculation is also easy. So here I would say that yg, it is a good practice to calculate this, calculate the center of mass at least once here. So yg, and let's actually start with xg. So xg, which we said that it should be 0. Let's see if it is actually 0. So this is basically x dm over dm. So the integral of dm would be m, the mass of half a disk here. And here for x dm, so we are assuming that the mass distribution is homogeneous. For this half a disk, I can say that dm is just density times area. So I would say that this is equal to x, and for dm I would say rho dA, where rho, or actually let's write it here. So rho is density, and it has a unit of mass kilogram per area, because we are in 2D, kilogram over meter squared. So now that we have, and this is a constant here, because again we are assuming that the mass distribution is even. So this would be equal to rho x dA, and for dA I can say that this is dx dy over m. And you can see here that this would be again rho x dx, and or actually it is better to take this into polar coordinate, or you can see that the boundary on x would be kind of like from minus something to plus something. Let's actually just use this. So this would be, let's say, from minus r to r, and this would be dy. It would be from y equal to 0 and from to the square root of r squared minus x squared. because basically we are saying that we are integrating from x minus r to x equal to r, and for y it would be from y equal to 0 to this curve, which the equation for this curve, so for a circle we have x squared plus y squared is equal to r squared, not plus. So this would be equal, and then we have y would be plus minus square root of r squared minus x squared. And because we are in upper half of the plane, so we should go with the plus sign. So y would be plus square root of r squared minus x squared. So you can see here that this integral would turn out to be 0, and therefore this whole thing would be equal to 0. So the x component of center of mass would be equal to 0 without actually doing the integration. So and actually I have to say that here also we have a kind of like even function of x, which would be multiplied by an odd function of x and then a multiplication of, so it's better to write it down here. It's not accurate to say that because this is equal to 0 and therefore this is equal to 0, because we have to do this integration first. So this would be rho over m integral of minus r, and this would be x r squared minus x squared dx. And now because this function is odd, so odd function of x, and because we have kind of like symmetric boundaries for x, just minus and positive, this integral would be equal to 0. So anyway, x of g is equal to 0. So we could also say that just based on symmetry, but it's good to do the calculation once at least. So for the y component, yg, again we have the same thing. So this would be y over dm integral of dm. So this would be m, and again this would be y rho dA. And now actually it's simpler to just take this integral into polar coordinate and do the integration in polar coordinate. So for polar coordinate, I can say that this is equal to m rho, and y in the polar coordinate would be r sine theta, and dA would be r, the kernel for the integral would be r, and this would be r dr d theta. So we have rho over m integral, and also integral of, actually let's separate them. Now we can separate them. So this would be r squared dr, and integral of sine theta d theta, and r would be from 0 to r, and theta would be from 0 to pi. So we are going to have rho over m, this would be r cubed over 3, and this would be minus cosine theta, then it would be cosine pi minus cosine 0, so the whole thing would be 2, so this would be 2. So this is 2 rho r cubed over 3m. And now let's calculate, let's actually expand this mass, or just calculate the mass of the half a circle over here. We can say that m, what is the mass of half a circle? So m, it is half of the mass of a full circle. So this would be half of, and the mass for the whole circle would be its area pi r squared times its density, which was mass, which had a unit of mass per unit area. So this is the mass of half a circle. So pi r squared rho over 2. And if we substitute this here, we get y of g. Remember, this was y of g is equal to 2 rho r cubed over 3 rho pi r squared over 2. So here we can cancel out the rows here, and also r squared with 2 of these powers. So we are left with 4r over 3 pi. So this would be 4r over 3 pi. So basically the center of mass for a half a circle would be somewhere here, and that distance from the center here would be, let's use another color here. So this would be 4r over 3 pi. The x component is 0 and the y component is this. And because we were measuring y from center here, so this distance would be 4r over 3 pi. This is a good number to just keep in mind, because it just appears in problems on half circles, problems that we have that are on half a disk or half a circle. So it's a good number, and as we will see, it is also useful. We need this number for calculating the potential energy. Anyway, remember our goal was to calculate the moment of inertia about point A, IA. And we said that we don't have IA. The only thing that we have for a half a circle is just IO, the moment of inertia about its center. It's just 1 over 2 mr squared. And in order to use the parallel axis theorem, we had to find the location of the center of mass, so that then I can use the parallel axis theorem between these 2 points and find the moment of inertia about this point. So this is center of mass. And once we have that, let's actually write it with green. Once we have IG, then we can use the parallel axis theorem to find IA. So this is a kind of a long way, but the calculation is just straightforward. Another way just to calculate moment of inertia is just do the integration for moment of inertia about this point. So that's always an option to use. But because we had this number for the moment of inertia about the center, we wanted to figure out the IA based on parallel axis theorem. So here I can say that IO, so let me actually bring this figure down. So let me copy this. Oops, doesn't bring the circle. Forget about it, because I have copied this. These are on 2 layers and it's just going to be pain to copy it. So basically I would say that IO, the moment of inertia about point O, is equal to IG plus this plus m times this distance squared. So this is the parallel axis theorem. So IO is equal to IG plus m times 4r over 3 pi squared. And now we have IG, we can calculate IG. So IG is equal to IO minus m 4r over 3 pi squared. And if we substitute for IO, so this would be IG is equal to 1 over 2 m r squared minus r squared, again 4 over 3 pi squared. And now that we have IG, I can calculate IA. So I can say that IA is equal to IG plus m d squared, and d is the distance between point G and A. So this is d, which again we can find out d based on the radius of this circle and also this 4r over 3p. So basically this is r, and we can say that this is a right angle triangle and we can write down d squared is equal to r squared plus 4r over 3 pi squared. So this would be, we have ig over here, so this is 1 over 2 m r squared minus m r squared 4 over 3 pi, the whole thing is squared, plus m d squared, and for d squared we saw that it is equal to r squared plus 4r over 3 pi squared. Therefore IA is equal to, so it would be mr squared, here we have 1 over 2, here we have minus 4 over 3 pi squared, here we have 1, and again we have 4r over 3 pi squared. So we can cancel out these two with each other, and we get 1 over 2 plus 1, that's 3 over 2, so this would be 3m r squared over 2. So that's IA. Okay, so now that we have IA, we can write down the kinetic energy T1, which was 1 over 2 IA omega squared. And omega, remember omega was V naught over R. So I can say T1 is equal to 1 over 2 I, which is 3m r squared over 2 times omega squared, which was V naught over R, or minus, doesn't matter, squared. So we are going to have 3m V naught R, V naught squared, or actually the R also cancel out, so we don't have any R here. So this would be 3m V naught squared over 4. And the unit also makes sense because it is kinetic energy, it's energy. So mv squared, we know that it has a unit of energy. So let me check this. We had 3 over here, 4, and basically, so that makes sense. So that's for T1. And now we have to calculate U1. For potential energy, we have to have a reference. Let's consider this bottom line as a reference for potential energy here. So if this is the potential, the reference for potential energy, we have to calculate the height of the center of mass from this line. We know that the center of mass, it is on this line here, 4r over 3 pi from this point O, and it would be just r about the radius of the circle above this reference line. So if this is a reference line, so this is the reference line, and G is here, we can say that the potential energy would be just m times the height of this point, the height of center of mass above the reference line. So that would be U1 is equal to, let me actually write it here. So U1 would be just mgh, which here is just r. Okay, so that's T1 and U1, that's basically E1. And let's calculate T2 and U2 at this moment here. So again here, to calculate the kinetic energy, we can do the calculation based on any point, but I would say that this point here that we have contact is just easiest point to consider, and that's because the velocity of this point is equal to 0. Because we have pure rolling, the velocity of ground is 0 here. So this point on the circle that is in contact with the ground should also have a velocity of 0. So the velocity, let's call this point C. Let's say this is point C. The velocity of point C is 0. So I can say that T2 is equal to 1 over 2. That's not a good one. Okay, so 1 over 2 m vc squared. So that's the velocity. Sorry, this term is equal to 0, so I should just write down 1 over 2 ig ic omega 2 squared. And now the key here is again to find ic. So we have to do the same thing here. So if you wanted to just calculate the moment of inertia about this point by having just the moment of inertia about point O, first we have to go center of mass and then go to this point. But because here we have ig, we can calculate ic easily. So ic would be, so I c here is equal to ig plus m, the distance between c and g squared. So this whole thing is just r. This is 4r over 3 pi. So this distance between c here and g would be r minus 4r over 3 pi. So this would be r minus 4r over 3 pi squared. So basically ic is equal to ig, which was here, we had it over here. Ig was this number, so mr squared 1 over 2 mr squared minus mr squared 4 over 3 pi squared. So that's ig, and here we have plus mr squared 1 minus 4 over 3 pi squared. So basically we are able to find ic. And now that we have ic, we can calculate the kinetic energy at the position 2. So let's say that this is something that we can find. So that's for the kinetic energy, and now let's find the potential energy for U2. So U2 would be mg times h, which is measured between the center of mass and the reference line. So here I have to show this. So let's say this is this line we have here, and the center of mass, we saw that it's just somewhere here, that this is 4r over 3 pi. So the height of this point above this reference line would be again r minus 4r over 3 pi. So this would be mg times r 1 minus 4 over 3 pi. So now we have everything. Now we have U1, T1, U2, and T2, and we should be able to find omega 2 squared, because the only thing that is unknown in these equations is just omega 2. So if we write down T1 plus U1 is equal to T2 plus U2. Remember, all of these values, T1 and U1, they're going to be numbers. So if we plug in the values, we have the numerical values for M, R, and V0. If we plug in those numbers, we find we should be able to calculate T1. Where is T1? So basically this is T1. And we can actually do this calculation, but I just leave it up to you guys so that we can solve more examples. So if you plug in the numbers here, you get a number for T1, because we have everything in this equation. And then for U1, Again, we have everything. mgr, g is 10, m is I think 4 kilogram, and r is, what is r? R is 3 meter. So I can do at least the first part and just leave the second part to you, for you guys. So T1 would be T1 is, where is it? Lost it. 3mv squared over 4. So I would say that this is 3 times m, which is 4 kilogram, times v naught, which is 2 squared over 4, plus u1. And u1 is mgr, which would be 4 times 10 times r, I think was 3 meter. So let's check for that. Yeah, r 3 meter and v naught is just 2. So that's for the left hand side of the equation. For the right hand side, we have T2, which would be a long term because this IC is a long term, but basically, again, we have everything to calculate this. So this would be T2, which we can calculate this value, plus U2, which is, so let's write this way. So this is 1 over 2 IC omega 2 squared. And IC is known. Plus U2, which is this number, 4 times 10 times R, which is 3 times 1 minus 4 over 3 pi. So you can see that in this equation, the only unknown is just omega 2, and it's an algebraic equation that we can find for omega 2. So solve for omega 2. So this is basically for this example, and just as a practice, you can give it a try to see if you can solve this based on Newton and Euler, and then compare the procedure to see if using the work and energy principle is easier for this problem or not. I would say that it is, and that's basically the power of this method for solving, again, some problems, not all problems, but it is good to have this method in our toolbox to be able to see, okay, this is a problem for work and energy, this is a problem for Newton and Euler approach. We should be able to, after solving few examples, we should be able to recognize these problems from each other and then choose the right approach and do the calculation and solve the problem. So I will prepare another example to solve here. Here is the next example that we want to solve here. So we are asked to find VA, VB, and omega AB. So velocity of this slider A, velocity of a slider B, and also the angular velocity of link AB when theta is equal to 30. So here initially we have theta equal to 60 degree, and we want to see what happens, what is the velocity of AB and link AB when theta becomes 30 degree. The spring is at its rest length initially, friction is negligible. So here the slider B has an initial velocity of 7 meters per second, and you can see that if this velocity is in this direction, slider A wants to go to the left, and basically this angle decreases, and we want to see what happens to the velocities when 60 becomes 30. So again, this is one of the examples that we can use the work and energy principle. So far in this course, we have been able to analyze this problem if we have ignored, if we didn't consider any mass for the link AB. But here you can see that the link AB has a mass here. So this is where the rigid body comes in this problem. If we didn't have any mass for this link, we would be able to solve this just with the stuff that we had on particles. But here, because this link AB has a dimension, its length is 3 meters, and it also has a mass, we should be aware that we are going to need to use our formulation for kinetic for rigid bodies. So the constant of a spring is 200 Newton per meter. Mass of a slider A is 4 kilogram per meter. Mass of a slider B is 5 kilogram. And as we said, AB is 3 meter and AB is 6 kilogram. So I would say that here, because again we don't have any friction, this is a good example that we can use the work and energy principle to solve this problem. So I would say that the work of non-conservative forces is equal to E2 minus E1. And because we don't have any non-conservative forces here, basically this work is equal to 0, and we are going to have conservation of energy. E1 is equal to E2. So let's calculate E1 and E2, and we should be able to come up with an equation on the velocities of these sliders, or the angular velocity of the link. So for E1, I would say, so E1 is equal to T1 plus U1. So for kinetic energy, let's start with kinetic energy. T1 is equal to, it would be the kinetic energy, sum of the kinetic energy for all the masses that we have in the system. We have two particle-like masses here, A and B. So their kinetic energy would be 1 over 2 ma VA squared plus 1 over 2 mb VB squared, plus the kinetic energy of this rigid body. And here is an example that we should be very, very careful about the point that we use as a reference, because there is no stationary point on this link. Both of all the points on this links are moving basically. We can, if we use the formulation for kinetic energy about point A or B, we have to be aware of the extra terms that we have on top of 1 over 2 mv squared and 1 over 2 I omega squared. So here I would just go with the safest option, which is using the center of mass for this link as a reference point for calculating the kinetic energy. So I would say, so let's show this point here. So this is the center of mass, for example, G. So I would say if I use G as a reference point, so this would be 1 over 2 m AB Vg squared plus 1 over 2 Ig omega squared. Okay, so at this initial position, at state 1, we have the velocity of this slider, and based on kinematic we should be able to figure out the velocity of A and also the angular velocity of the rigid body of the link. And there are several ways that we can do it. One is just to use the vector notation to say that, okay, write down the velocity of A based on velocity of B. The omega would be all unknown, but we can apply one constraint, and that is the velocity of A should be in the horizontal direction. And based on that constraint, we can figure out the angular velocity and also velocity of point A. But another approach is to use the concept of instantaneous center of rotation. So for this system here, we can easily find the instantaneous center of rotation, and if we have that, we can basically write the velocity of A based on the omega of link. So I would say that to find the instantaneous center of rotation, we said that if we have the velocity of 2 points on a rigid body, and if we draw the line perpendicular on those velocities, the intersection of those perpendicular line should be the center of instantaneous center of rotation. So here I know that the velocity of point B is in the vertical direction, so perpendicular to this direction would be horizontal direction. And for velocity of A, it is in the horizontal direction, and perpendicular to its velocity, it would be in the vertical direction. So basically this is the center of rotation here. So instantaneous center of rotation. Let's show it with IC. And now that we have this, we can basically write down the velocity of any point on this rigid body based on its distance from this point and the angular velocity of rigid body. So I can say that VB is equal to, let's call this point, for example, C. Let's just call it C. Velocity of B would be BC times omega. So this would be BC times omega. Velocity of A would be AC times omega. So AC times omega. And same thing is true for VG. So VG would be CG times omega. So here we have the velocity of B, we have also BC, we should be able to figure out omega, and once we have omega, we should be able to figure out VA and VG. So basically here I would say that omega is equal to VB over BC. And this is, so VB is 7 meters per second, and BC, because this angle is 60 degrees, so BC would be AB times cosine 60. So this would be 3 times cosine 60, which is 1 over 2. So basically this is 14 over 3. And now that we have omega, so this would be in radian per second, we should be able to calculate VA. So VA would be AC, which would be 3 times sine 60. So this is 3 times sine 60 times omega, which is 14 over 3. So sine 60 is square root of 3 over 2. Here we can cancel out the 3's here. So this would be 7 square root of 3 meter per second. And VG, for VG, we have to find the distance CG. And here, because G is at the center of this link AB, we know that in a triangle, in a right angle triangle, if we connect this corner to the middle of the hypotenuse, this distance should be half of the hypotenuse. So if AB is 3, this should be 1.5, 3 over 2. So little geometry here. So if that's 1.5, so here we can say that this would be 3 over 2 times 14 over 3, which is omega. And this would be 7. Again, meter per second. So now that we have all the velocities, we should be able to calculate this term. And the only thing that we need here is just IG, which we know for a link is, let's write down IG. So IG is ml squared over 12 for a link that is long and the other dimension is small compared to its length. And when we are calculating the moment of inertia around the center of mass here. So this would be m, which is 6 times 3 squared over 12. So this would be 9 over 2, which is 4.5. So basically here we can calculate T1 here. It's just we have all the parameters. So that's for T1. Let's calculate all the other terms and see if we have time to plug in the numbers and calculate the final answer for it. So that's for T1. Let's also calculate U1, the potential energy at state 1. So I would say for U1, this is equal to, remember this was the potential energy due to a spring plus the potential energy due to gravity here. And here the direction of gravity here is just in this direction. So for a spring, here we have a spring here. Because the spring is at rest initially, there is no energy stored in the spring. So U spring would be equal to 0. But for gravity, we have the potential energy due to gravity. We have to have a reference line. So let's say this is our reference line. So therefore, particle A wouldn't have any potential energy due to gravity, but particle B and also link AB have potential energy due to gravity. So for particle B, we can say this would be mg times this height, which is basically 3 times sine 60. And for link AB, we can say that it's mass times g times this height, the height of the center of mass from the reference line, which is basically half of this distance. So it is 3 times sine 60 over 2. So I would say that, so MA is 4 kilogram, MB is 5, we need MB. So this is equal to 0 initially, so we are gonna have MBG times H, which is 3 sine 60, plus MABG times 3 sine 60 over 2. So that's the potential energy at the initial state. Now we have to go to the second state, E2, calculate E2, the energy at second state. So again, we have the same thing. E2 would be kinetic energy plus potential energy. So E2 would be T2 plus U2. So let's start with T2. So for T2, again, we can say that this is equal to 1 over 2 mVA squared, and let's say VA2 plus 1 over 2 mVB2 squared plus, again, I use the center of mass as a reference point for the link AB. So this would be 1 over 2 MAB VG2 squared plus 1 over 2 IG omega 2 squared. And now the key here is that, again, we can use that concept of instantaneous center of rotation and write down VA, VB based on omega. So if the angle is 30 degrees, remember these equations that we had over here, they are again true, but we have to just change 60 to 30. So at the state 2, I would say VB would be BC times omega. So basically here I'm saying that, let me draw the triangle here. So let's say this is this side, and also this side. So this angle now is 30 degrees. 30 degree. This is A, this is B, and center of rotation would be, again, we have to draw the normal from here and also normal from here. So this would be the center of the instantaneous center of rotation. So, and G would be here somewhere on AB in the middle, so that's G. So again, BC here would be this side, AB, which is 3 meters, times cosine 30. So this would be 3 cosine 30 times omega. For VA, I can say that it would be AC times omega, and that's 3 sine 30 times omega 2, omega at the state 2. And for Vg, so Vg2 is equal to, it would be Cg times omega, and again we can use our little geometry trick here, which Cg should be half of AB, and therefore this would be 3/2 times omega 2. So therefore the kinetic energy just in the second state would be a function of omega 2. And when we find omega 2, we can substitute it back into this equation and find VA and VB. The question asks for all these three variables, VA, VB, and also omega 2. So these are VB2, VA2. And IG is just the same thing, ml squared over 12. So that's for T2. Let's also calculate the potential energy. So basically, let me write down here that T2 is T2 of omega 2. It would be a function of omega 2. Let's calculate the potential energy. The potential energy, again, we can say that U2 would be U spring plus U gravity. And now the spring is just compressed here. So there is a change in the length of the spring, and therefore there would be energy stored in the spring when we have to account for that. So how much the spring is compressed here? We can say that 3 times cosine 60 minus 3 times cosine 30, because that's basically how much this mass is moved here. So I would say that this is 3 cosine 60, and when the spring is compressed, the mass would be here, and this side would be 3 times cosine 30. And the difference here between these two values would be the amount that the spring is compressed. So I would say that this would be 1/2. By the way, let me check if we have K, spring coefficient. Yeah, we have it, 200 Newton per meter. So this would be 1/2 K delta squared, the change in the length. So this would be 3 cosine 30 minus 3 cosine 60 squared plus. For UG, I can say that this would be again the potential energy of A, B, and also link AB. The potential energy of A again is 0 because its height doesn't change. Its height from the reference point doesn't change, so the potential energy due to gravity for A is equal to 0. But for B, we do have a change in the height compared to the reference line. So this would be, if this angle is 30 degrees, the height of B compared to the reference line would be 3 times sine 30. So basically this would be BG 3 sine 30 plus AB G 3 sine 30 over 2. Similar to what we had for state 1. Just over there it was 60 degrees, here it's just 30 degrees. And again here everything is known in this equation. We can calculate US, we can calculate UG, we have all the masses here, and also the spring coefficient. So U2 is known here. So basically I can say that T1 plus U1 is equal to T2 plus U2. And we saw that this is a function of omega. So this quantity is known, this quantity is also known, this quantity is also known, and there is one unknown in this term, and that is omega. So if we substitute all the numbers, which I leave it to you guys, we should be able to find omega. And once we have omega, then we can say VA. So here the output would be omega. And once we have omega, I can say that VA is equal to, in a state 2, it would be AC, which was 3 sine 30. So that would be 3 over 2 times omega. And VB would be, I think, 3 cosine 30. Yeah, 3 cosine 30 omega 2. So this was omega 2, basically. Omega 2, and 3 cosine 30, that would be 3 square root of 3 over 2 omega 2. So I hope calculating this is not that difficult. I don't think it's difficult. It's just plugging numbers here. So yeah, that's it for this problem. Just we write the conservation of energy. We were able to find omega 2. We should be able to find omega 2, and once we have omega 2, we can calculate the velocity of the other particles that we had, and that's all we are asked to find. So yeah, I guess that's it for this problem. We just solved it. So I guess I see you guys in the next lecture.